Okay, I believe we are recording and making progress. So we finished up last time by going through in a lot of detail what happens on these graphs with the with the animation that shows us the various points along the way. And we can come over back to that again if you guys need to. You just need to let me know if it's continued point of confusion, particularly when you get a homework problem or two. If we need to do a little separate one, we can. It's really the core of the course to understand what's going on between two devices that don't really have any idea of what's happening in the middle. So we've started at the top and we're kind of working our way down, and that's the last point we leave the host with end-to-end communication. And so what's going to happen after this is we're going to start breaking into more of the network layer. Unlike the transport layer, which we just left, the network layer runs in all the routers as well as the end hosts at either end. So there's a copy of IP and all the other pieces of layer 3 running in all of the routers. And if you remember the diagrams that I think we've all seen before, we've got these various devices that each have 5 layers in them, and you're told some of them are routers and some of them are just hosts at the end. The hosts at the end, they go like this, and in the routers you only go up to layer 3, and then you've got applications talking to applications here, and you've got transport layers talking to transport layers between the two, but everything else in between, it's layer to layer to layer. So there's a pair here to here, one here to here, and one here to here. And so this task of getting packets from one end of the network to the other now falls to getting it from one device to the next, and it has to make a decision based on the fact that maybe it has lots of different paths out to connect to lots of other networks. If it chooses this one, then that's what this represents, is just that one. It doesn't mean that it only has one way in and one way out. It's just for this particular route what we're doing. So that's kind of what we're going to dig in more about and talk about. The reason why there's a 7th edition of the book, as I think I may have mentioned, is they split what was layer 3, chapter 4, into 2 different chapters because of something profound that's happening in the design of these systems, which is to extricate just the data processing responsibility away from the router and leave it with just the high-speed routing and move that data processing part into the cloud where everything else is moving. So why not the work that's happening at a router as well? Okay, so we call those 2 halves a data plane and a control plane. The data plane is where all of the data is being massaged and moved around, et cetera, and the control plane is the one that's making the decisions to kind of guide it. Here's how you need to move things around. So we'll take a look at what's inside a router. We'll take a very deep look into IP, and then we will advance forward from that and look at some more ways of generalizing what's going on, and that'll lead us into the next chapter as well. So we want to understand what's different about this layer, the network layer, than the transport layer that we had before. We also want to know the difference between just forwarding a packet along and actually running a routing protocol. And we'll take a peek at one example of using these protocols, which there's no better example than the internet itself. And so that's what we'll do. So the transport, the network layer has a responsibility of taking packets from the transport layer and then moving them from location to location. And because the font sizes are a little weird here, it ended up lining these things up kind of in the wrong boxes. So let me fix that real quick. On the sending side, the application gave data to the transport layer, maybe TCP, maybe UDP. It did whatever preparations were necessary and then gets it down to the network layer. And so the network layer starts the nitty-gritty task of sending things along. And so we use this idea of taking things that we get from above and putting them in an envelope and adding our own addressing onto the front. Maybe we put other people's stuff in there too and sending it along. So this putting it in an envelope or putting it inside of a capsule, if you're talking about putting little little grains of some sort of medicine inside of a pain reliever capsule, if you will. We call it encapsulation. We're basically encapsulating, putting things inside of capsules or putting things inside of envelopes. We could have called it, I guess, an envelopulation or something like that. Maybe we should make a new word here. So the network layer runs in all the routers and in the computers on the end as well. All right, so two key functions. One is forwarding and the other one is routing. And forwarding is the task of taking a packet and more or less mechanically, although we're dealing with bits, not atoms here, so it's kind of electrically really, but mechanically taking these bits and extracting them out of the input buffer on a line card that's coming into one side of your router and moving them across your electronic fabric and getting them into the queue, into the buffer that's waiting to send things out one of your output circuits, out of one of your output lines. And so that's an extraordinarily high speed, very expensive proposition. And lots of intellectual property, meaning lots of new inventions, have taken place around that. It's been a core feature of Cisco's success and of other people's demise. And there's there's lots of companies that are making these. Juniper's one that's very successful as well. But this is something that's handled by a small handful of large companies for the most part. So that skill of knowing how to design things to without as minimal delay, without as any delay at all, if you can pull it off, get things from one buffer into the next is what forwarding is dealing with. So if this is like taking a trip, if that's the analogy we want to use, this would be like quickly deciding when it's time to get from 610 to I-10, how quickly can you make that transition, right? When Waze tells you in 300 meters, take a left to get onto I-10 North or I-10 West rather, than that's something that you want to do. Of course, during rush hour, it can just sing its little head off. It's not going to do you any good. The other function that this layer does, which has traditionally been inside of a router, but you notice they're being careful to just say it's the layers functions now, because we're going to start splitting these things, is the decision making. Whose decision was it to get us from 610 North to I-10 West? Who made that suggestion that was the exchange we needed to make? So the routing algorithm has that responsibility, and routing is the task of making those decisions, sending you on a route, like a travel agent might program a route, plan a trip for you from one point to the other. And you may go over all different kinds of technologies, Ethernet, Wi-Fi, wireless, wired, optical, etc. Just like on a trip, you might go from Uber to bus to plane to train to ferry boat to whatever. Right? So we're dealing with who's making the decisions on where to go and where to send your packet. So we break this thing into two layers, the data plane and the control plane, and we look at the very beginning of a packet as it arrives, because that's where we put the address, the destination address of where we want this packet to go. So we get an early look at it just as the packet's arriving. We don't have to wait for the whole thing to arrive. In fact, the rest of it's still kind of racing in, but we can already get a jump on making a decision about where we want to send it. In this particular example down here, we decided that as this packet arrived, wanting to get to address 7, that the way that we chose to do it was to send it out physical port number 2 on our router, out of maybe 3, out of maybe 200, who knows. But this idea of moving the data around has to happen locally where these cables physically connect with each other. It can't happen someplace else. It's got to happen right there where the two connections are made. So this is a local function that can be done inside and must be done inside of every router. All right, so this is kind of forwarding the thing along. The control plane, that logical construct, the control plane of the router is something that's sort of across the entire network. This is the smarts that are inside of a program like Waze that sees what's going on all roads in all parts of Houston, and it's getting data constantly up in a data center. It's analyzing all this stuff and combining it all together, and it's giving you the advice that this is where this is why I'm telling you to go left, to go right, because I see what's going on and I'm making the best decisions on an overall basis. So this is a big picture view, determine how the datagram is routed among routers. And there's two ways of doing this. There's the traditional way of doing it where that software is implemented in the router, and the router takes time to gather data on what is around it, and that it also learns from the routers that are near it what other routers are near them, and on and on. So it does this in sort of a propagation type of fashion. It may take you quite a while by going round after round of exchanging data with ever increasingly further away routers to learn a substantial part of what the network looks like. On the internet, you never know what the whole thing looks like. It's too big. It's impossible to do it. But that software runs inside the router, and it's what makes the internet work to a large degree today. The other way of doing this is what's called software-defined networking, and this is the new kid on the block. And the unquestioned leader in moving in this direction is AT&T, at least from a commercial enterprise. They've moved the vast majority of their network control over into this scheme where not just for routers, but for all kinds of information forwarding equipment they've got at all different layers, they are standardizing on gathering information on how things are connected together and how they want to allow things to get forwarded, and they are making those decisions kind of in the cloud and then pushing the decisions out to each individual device on what to do. It also has this huge breakthrough ability at letting customers log into one place and see a view of all the devices, and they can make kind of logical decisions like, I would like to have access to the AWS data center in Hong Kong because I want to push some applications over that way. You know, you would have had to know in tedium every little step along the way, but now that you've got everything in one spot logically in a database, you can start building kind of abstractions on top of it and giving people this vision that they can have one view of your entire network, which is all the AWS data centers. Well, that's not at all what AWS has built, but they can extract from all the millions, if not billions, of connections they have something that shows you, just that customer view of what's going on. So it's incredibly powerful. It's carved hundreds of millions of dollars of expense, as it has for other people who have gotten that deep into it as well. And that's a total software definition for modeling what the network looks like and how to put the pieces together. What is a little more restrictive for us, we have a little narrower view on this with software-defined networking. We're restricting this view to routers only. But even there, it's a breakthrough. And we'll talk more about the kinds of things it lets us do that we haven't been able to do before. So if you've got your control on a per router basis, which is the existing, for some people it's old-fashioned now, but it's still the super dominant way of doing this. What you have is in smarts at every point along the way. Every router has an algorithm, a routing protocol that's being used to decide who's near and who's far and who can I reach, et cetera. And what these routing algorithms will do is they exchange data with each other, as you can see with these arrows across the top. And periodically, they have an update that they wish to give to the data forwarding part, the data plane part of the router. And so they will push down updates in the form of a table that say, if you want to get to this network, go out this port. If you want to get to this network, go out this port. Otherwise, if you don't know, and I don't have an entry, then just try sending it out this port. So that's the area where the routing algorithm produces something. It produces a routing table. Nothing happens without the routing table. Every input port has to have a routing table to tell it how to know how to forward the packets. No routing table, no way of making the decision. So the critical output of this top part of the routing algorithms is to produce these routing tables. There's no time at all for a packet to come in and for you to send a question up to the routing algorithm and go, what do you think? Left or right at Albuquerque? Things are happening much too fast for that. So we pre-build the routing table and we push it down into extremely high-speed memory. All right, so you can kind of logically draw a dotted line through here, but they're really in the same device. But we do separate those two. There's different specializations. There's different types of technology. The top part is just a regular Intel Linux-based server, and the bottom part is secret sauce, lots of special gear. So you can have a a centralized control plane if you want, which is kind of the other way of pulling this off, where you do everything in the data center, at least as far as the control plane is assumed, and you just leave in the field, you leave in the routers the act of actually doing the nuts and bolts forwarding. So you still have to push a table down. You still have to let every router know what to do, but you're not going to make the router figure that out for themselves. You're going to figure it out for them and hand them the answer. And what you need them to do is maintain a connection back to you so that if things change on the network, whereas a routing algorithm that was running on the local router would have been right under its nose, it would have seen it happen immediately, it could have recalculated a new routing table. If a link went up, a link went down, you discovered a new network, you forgot about one, etc. Now it's not instantaneous, because now the people that need to know this and act upon it and calculate it are in some far off remote data center. And there's a little bit of risk there, because if the part of the network that went down was the part that you used to talk to that data center, then you have no way of getting the update there. But you can limp along for a while on your own. You don't have to have an update every 5 seconds. So the way of drawing that's a little different. When we get a packet in, we still have the task of forwarding it, but the forwarding tables and the switching fabric still live locally in the router. The control plane is now isolated, separate in another part of the world, running in some data center someplace else. So we need a piece of software left behind that has all of the hooks that would have been used to grab information from what the routing of what the forwarding part of the router sees is happening, get those updates, to ask queries, and you need the hooks to push changes, push updates into the routing table. So we'll leave behind a small piece of software called a control agent, a local control agent in every one of the routers, and it's going to have the responsibility of sort of maintaining communication. This was sort of like, I suppose, introducing HTTP as a way of gaining access from one local PC to data that's now sitting someplace else. You could have had all that data on your one computer, but now you want these things separated, so you need some software to kind of help make that happen over the network. All right, so what does the network layer do to try and make itself useful to programs and layers above and below? What's its service model, in other words? Is it a channel for transporting datagrams one into the other? An example of something it could do is guarantee delivery, or guarantee delivery in a certain amount of time, or that certain packets get prioritized over others and therefore suffer fewer changes in separation between packets. If you need the packets to show up like clockwork, then like voice or video maybe that's a service the network layer could provide. You can design your infrastructure to support these types of services. We'll see when we talk about the internet that it does very little of that, because it was considered a lavish expense at the time and people didn't really want to invest in it. So services for individual datagrams might be the delivery guarantee. Services for an entire stream of datagrams is they're going to show up in order, and I'm going to make sure you can get at least this many packets a second across, and that inter-packet spacing is that clockwork I was talking about just a minute ago. So there are technologies that can pull this off. The internet is not one of them. It's not something that it's widely capable of doing. There may be pockets where people do some of this stuff, but it's mainly done inside of institutions. But there are other network layer technologies besides just IP. ATM is one of them, not automated teller machine, but asynchronous transfer mode, 53 bytes, 48 payload in every packet. And they actually offered a series of service levels. They had one called constant bit rate, where it's just like it sounded, never more, never less, perfect for applications that need an absolute constant amount of data, like a high resolution video stream leaving Toyota Center and making its way via fiber back up to New York to be shared with the nation. That would be a constant bit rate application. Variable bit rate, fluctuate a little bit, but you're guaranteed a certain amount of throughput. But it does have some wiggle room. ABR is maybe adjustable bit rate. Some people will call it other things as well, but this is one that says, look, I'll guarantee you a certain minimum. If there's less stuff going on the network right now and there's some bandwidth free, I'll let you burst up and use more of it, but never less than that. And then unspecified bit rate is one that says, send me some bits and I'll get to them when I can. Very much like internet. So the UBR layer of ATM corresponds to the top row in the table, which is what the internet does, which is best effort. The difference with ATM is it keeps things in order, and the internet makes no such guarantee. Okay, so moving right along. What's inside a router? We've talked about the cards on the left, the cards on the right, the input parts on the left, the output parts on the right. You have your routing program that runs above that horizontal dotted line. That's the data plane where you are trying to figure out what's going on, build a table, build a routing table, and then push it into the cards. And believe it or not, it's actually pushed into each individual line card. As crazy as that sounds, because there's no time for those line cards to compare notes or to do anything like that. So you're going to push everything you can in there. So the input card is responsible, therefore, for three things: physically terminating the line, electrically, optically, via an antenna, whatever it might be, getting the bits off the medium and into the link layer protocol. So they're grabbing the individual ones and zeros, cleaning things up if they need to. And the data link layer, like Ethernet, for example, which we'll get to, is responsible for sort of figuring out where in this stream of bits the beginning of an Ethernet frame is. So there's a special pattern that's looking for in the bits to tell it that that's happened. Grab all the data together, figure out what it's really for you, and what's down inside the envelope, inside this encapsulated package, who's it for up above. But in the meantime, you're looking to see where you want to send this thing. So you're digging around quickly inside, looking at the destination address and deciding who it needs to go to. And that lookup is done by a table and some smarts that are inside every line card. We don't do that in one single place in the router anymore, despite the fact that that makes maybe perfect mental sense, for the simple reason it's not fast enough. So we turn each one of these line cards into their own partial switch to get things done. If the data is showing up faster than you can get it across the switch, you need some buffer memory here to buffer things. If it's going to be the case that you're going to have to throw the packet out once it gets over to the output queue because the output queue is just completely overwhelmed, then for goodness sake, spot that early and drop it here. Drop it as it comes in the door. There's no point in continuing to process a packet if all you're going to do when it gets over there is throw him off the boat if you're not going to let him there. So there's some very important logic around the way those kinds of things work. So destination-based forwarding is what we mostly do on the internet. Despite all the data that's inside of a packet header, where it came from, the time, the protocol that it's running, any other type of bits that are set, the only thing we really care about is who are you trying to reach. Don't really care at all where you came from. Just want to know who you're trying to get to. I'm busy here. Just tell me where you're trying to go and I'll send you on your way. So that's a traditional way of doing it called destination-based forwarding. But there's also better ways of making perhaps more informed, better routing decisions if only you were to take a glance at more data than that. And we'll take a look at some examples of it. Okay, destination-based forwarding looks like this. And this is a pretty tedious topic, so make sure you take another drink of coffee or Coke without sugar and put your thinking caps on, because this one's going to require a little bit of effort. So I see a bunch of 32-bit addresses in this table. This is my forwarding table, the output from my routing protocol. And I'm going to push this down into every single one of my input cards so that they know that there are 4 output cards. And every time they get a packet, they're going to look at the destination address inside the packet, and they're going to decide based on this table whether to send it out to output card 0, 1, 2, or 3. That's the purpose of this table. So if I pop this in here, I said again, there we go. If I pop this in here, we're going to come back to it a few times. Oh, that way we won't. There we go. I don't know that I need to make it bigger, so let's just move it up instead. All right, and I'm going to walk us through some slides, but I'm going to keep coming back to kind of the same thing. All right, the first thing I notice in this first row is it's talking about a range of addresses. And they start off with the same bits. In fact, all the bits inside the orange block are the same in the top and the bottom part of this first row. 1100, blah, 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 blah. And at the very end, outside the orange block, where the arrow is here, I notice that I'm running the complete range of bit combinations, all the way from all zeros up to all ones. Forgive the highlighting. It's, PowerPoint trying to be smarter than it needs to be. So what I'm basically saying is, if I get an address, the only thing that really matters that I check are the bits that are inside the orange box, the first 21 bits, it turns out. The remaining of them are unimportant to me making the decision as an input card on the router as to which interface I need to send it out next. If it matches these first 21 bits, if the first 21 bits of the destination address of the packet that I've been given match these 21 bits, then I know I should be sending it out link 0. So I will immediately try to send the packet in that direction. All right, so you don't really need to draw all of that. You can actually make this a little bit easier on yourself by just pointing out. And let me see if I can use the same color they do. Get rid of some of these reminders here. All I need to really match is this. So all I really need to put in here is an entry that says if the first 21 bits start with this, then you're golden. The remaining bits can be anything. All zeros all the way up to all ones, anything in between that you can think of. 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 0, 0. The very last one's going to be all ones. Anything in that range will match this prefix. So I'm going to publish this as a route in my routing table. And I'm going to tell all my input cards, if you see something that matches these, go out link interface 1. All right? Awesome. That looks simple enough. What about the next badge? Two important things about the next badge. The first important thing is they also have a range, a continuous range of all zeros to all ones, but you'll notice this time it's a little bit smaller. And this time all of them start with the same 24 bits, not just the same 21. They all start with these 24 bits. So I could publish this as a second route and tell my input cards, if you receive a packet and you look at the destination address and the first 24 bits match this, then send it out link interface 1. Send it to output card number 1, because I've got all the combinations covered. The second important thing about this is it's adjacent to the one above. So this address on the top part, if you add 1 to it, the binary address you get is the next row. And so we can grab this part out here and I can show you. 0, 0, 0, 1, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. That's the first row, this one here. And now I'm going to add 1 to it. And what we're going to get is 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And the first 4 bits don't change. So if I look, that is exactly what I have here. And I've left off kind of the first 16 bits because they're not going to change, but these last 16 bits match this exactly. So that's kind of unusual that things have lined up, so terribly nicely that they're adjacent. They're adjacent like that. Okay, the third group is a little different still. It's got this sort of going for it. I have to get rid of, hold on, I have to get rid of that selection that I made. Okay, it has this going for it in that the last 8 bits have the complete range from 0 to 1s. Can't go this far because this is just fixed 1 to 1. And the other thing I'll point out is that they also, the top row and the bottom row look like they're going to go 24 bits, but it's a little bit different now. because you'll notice in here, things start getting a little more complicated. Always before, I had the same bits in the top part and the bottom part, right up to the point where I went all zeros to all ones. Look, this top one, the first 21 bits matched perfectly, top to bottom, until I got to the point where it's all zeros to all ones. That worked great for the first couple of rows of this, but now I'm to the point where I don't have that luxury anymore. Because what I see is that the first 8 bits match, the next 8 bits match, the next 5 bits match, and the last 3 do not. So what I'm taking a look at here, if I step back for a minute and see what's going on, I have a range of IP addresses here. This one starts with 0001 and all zeros. And this one at the very end goes 0001 and all ones. So I actually, between here and here, have the entire range of all IPs that start with the same first 16 bits as you see up here, 0001, and all the way down to 0001. And then after that, all zeros and all ones. It just so happens that they're broken up into 3 groups. The first group gets this, the next group gets this, and the third group gets from 1 past this, which is 001, all the way down to all ones. So it's a weird way to get there, but it worked. And it's also weird because they were adjacent to each other. Do you know what I mean? Like this is a single contiguous block of IP addresses at the end of the day. They don't have gaps in them. That will never happen in reality. You will always have routing entries that are completely non-contiguous all over the map with all kinds of, blanks between them. You don't know about all the IP addresses. Heck, all the IP addresses haven't been assigned out. So how could it be a single contiguous range? The other thing that makes that not matter, makes it not so important, is the fact that you're not routing them all to the same place anyway. So what difference would it make if you found out they were all together? So we've got kind of the basics lined up here on sort of what's going on. The rule is we can now simplify this table. We can just pull this guy out, and this guy out, and we only go up to here, here, and here. We can just replace the rest with asterisks, and that gives us this routing table. Right? Otherwise means you're never going to see it called that. You're going to see it called default. So this is known as universally as the default route. Okay, so you can memorize that. Sort of says otherwise, but people don't call it the otherwise entry. They call it the default route. Okay, so let's look at a couple of incoming IP addresses. These are packets that have shown up, and I've been asked to decide where they go. So I open up the IP header, I look at the source address, and I look at the destination address. The only one I really care about is the destination address because I'm using destination-based forwarding. So DA stands for destination address, and I start looking for entries in my routing table that match. Okay, this starts with the 1, they all start with the 1. All right, let's move forward a little bit. These all start with 1100, as do all of these. Oh, okay. What about 11001000? The same. They all match those. Let's add on the next 8 bits. They match those as well. Well, am I ever going to find a difference between these? Yes. Once I get to 0001, I've ended the parts that match all of these rows. They all start with 0001, and then they break away after that. So this first one, the next bit is a 0. And the only one of these 3 routes where the next bit is a 0 is the first route, the first row. Therefore, this packet needs to be sent over output buffer, output card, link interface, whatever you want to call it, number 0. And so it will get forwarded over to the queue to get that done. All right, what about the next address? Same kind of thing, starts off with the same first 20 bits. The next bit of it, though, is a 1. And that matches both this, that matches both this and this. So am I just supposed to pick my favorite, or how is this actually supposed to work? You know, The next 3 bits are zeros, so this is 1000. So this matches 1000, but hey, so does 1 asterisk asterisk asterisk. That also matches 1000. It matches any set of values for the asterisk. So how do I know which one to take? There's an important rule called longest prefix matching. And if you match the longest prefix, you're guaranteed to use as much of the destination address as possible to make the best possible decision about where to send it. So we will give up on the 3rd route in favor of the 2nd route for this particular packet as a result. And we'll talk a little bit more about why that's done. The longest prefix matching is usually done inside the router's input cards. It's a very expensive memory called ternary content addressable memory. And it's unusual. Normally what you feed all of your locations of memory is the address that you're looking for. And the one that has the address will recognize it and wake up, and he will hand you the data that he's got in storage. This works the opposite. You send all of the elements in memory, the contents that you're looking for. And the one that has the contents will stand up and announce his address. So what you hand this ternary content addressable memory, or TCAM memory, is the destination address that you've been given, and the one with the longest matching prefix will raise his hand and say, you know, I match 18 bits of that. And somebody else might say, well, I match 20. It's like, okay, well, you win. And that's how you'll then look in there and see which output link to use, and you'll forward things on. Extraordinarily expensive memory. Seems like it might be pretty buggy based on the Stanford paper I may have mentioned to you from some years back. But it's also in high competition because there's other types of devices that use this as well, like automated vision systems and machine learning systems and maybe some GPU related things as well. So it's been rough to get our hands on as much of this as we need in the industry, and it's caused just perpetual product delivery delays. We can never get stuff to people as fast as we want. A Cisco Catalyst switch, they can have up to 1 million routing table entries in TCAM on a per card basis. Switching fabrics, there's a variety of ways of actually pulling this stuff off. It's supremely uninteresting to me because it's a task that's got to get done, and you use whatever you need to get there. We don't have anything to do with programming any of that stuff. That's one area that I've managed to do hands-off, although ironically, I was up to my elbows in it at the phone company because we're a switching company. All right, so switching via memory, first-generation routers would get a packet in. They would see the destination address. They would hand it to the program, the routing program that was running in memory. So they'd actually hand the packet to memory, very quaint. It would look in its table. Maybe it would do a bubble sort or Newton's approximation or who knows what, and it would find whether it had the element in there or not. There was no TCAM in any of this stuff, and it would make a decision about where to send it out. So it would send a copy out the door. So your speed was limited by the software and by the bandwidth of the bus. So that, you know, that was fun. It's kind of worked okay, but not great. There's an animation in the book's website if you want to see it. Switching via a bus is something that makes it easy for all input cards to see all output cards because they all share the same bus, like riding on the bus together. The problem is there's contention for access to the bus. So you don't want to let one line input card kind of hog it up the whole time, or nobody else will ever get to send anything. But these buses are super fast. In a Cisco 5600 switch, the author points out that the bus speed is 32 billion bits per second. That's enough for enterprise routers, for large company routers, institutional routers. And then you've got this type of interconnection network. This is used in some other devices. Again, the author chose to mention Cisco's 12,000 switch. They have 60 gig through the internetwork connections here, but this one lets you do some stuff in parallel, like if this card is talking to this card, then this one can talk to this one because they don't cross paths with each other. Okay, so queuing is a key issue here. whenever something shows up at a router, there's a decent chance it's going to have to wait around a while to learn its fate and to wait for its turn to come to the front of the line. And so this is called queuing delay, and it's one of the two types of delay inside the router. It also is a source of loss. So if your input buffer fills up and you have no room for anything else, you just drop packets as they come in. And the fabric, if the fabric isn't quite as fast as the combined speeds of all the input cards, it's also possible for you to overrun the fabric and drop packets because of that. The next bullet on this is kind of interesting. It's called head of line blocking, and you'll hear this even today. It's a common issue now. What head of line blocking means is I've got two people at the front of their queues, and they each want access to the same destination. So head of line blocking is kind of an issue here because both the first and the third card want to get into the red card's output buffer. And you've got to pick which one to do. So you decide to pick orange will go to orange first. And while that's going on, you will let the bottom red go to the top red. And then in round 2, you've got the top red that can get to where he needs. So he's now in round 2 able to go. And the green one could get to where he needs. So in round 2, you're done with everyone except this orange one. So what would have made more sense in this case? Because you experienced head of line blocking, what would have made more sense in this case would have been to let this guy go first, this guy go first to his destination, and switch the order of these two packets in the input queue and let the green one go first. And then in round 2, all you have left is this guy and this guy. 2 rounds, you're done. This one you already sent. He's not there. Instead, what we got was we send this guy first. Let me switch colors so we can kind of, well, I'll back off of all this. All right. What we got first was he sent him first. This guy had to wait. And then we sent this guy first. He also got to go at the beginning. I'll reproduce my numbers over here. And that was all that could happen because he's blocked. Round 2, this guy can go here, and maybe this guy can go here, but I've delayed slightly the sequence in which things can get reliably delivered. So head of line blocking can get complicated. It's an issue, and you want to try and reorder things in your buffer if that's happening to try and get people out the door at least as fast as they can. Hey, why'd you let him cut? Because there's no line where he's going. All right, output ports also have buffers, and if you can't get the packets out the door at as fast as they're coming in, eventually your queue fills and you start throwing away packets. There's some animations in the book that we'll look at in the homeworks that will show this to you, but I'll show you one of them. It was a sneak peek. You may have seen this already, but I'll pull this up. I think this is it. This is all the way back to chapter 1, if you guys remember, but I'm going to show it to you. Again, let's say I have 500 packets a second arriving and 500 packets a second transmitting. And so I wish I could just like make this thing super fast, but these things will start buffering. In fact, I can make this thing, let's make it a little easier. So it's definitely going to start queuing right away. What you don't want to do is wait to figure out that you're going to have an output queue problem until you have an output queue problem. If you can keep in touch your output ports and your input ports, the input port should know, like, hey, I'm getting ready to send this guy over, but isn't he like swamped? Isn't he totally busy? You know, what's going to happen there? And what you may have to decide to do is pick who's going to get to go through and who's not. So what some devices will do is they'll just optimistically throw away some packets at the input and relieve everybody of congestion. You reduce head of line blocking, you reduce the need to queue stuff, you reduce the wait times in the switch, you shorten the size of the buffers in the output queues, so you can kind of throw people off the boat, you know, right as they get on. You don't have to wait until you're in the middle of a storm. So that's one way of approaching something like that. And it's very impactful to the overall throughput of your router. So your scheduling discipline will choose among which of the datagrams in the queue get to go next. And you can implement things like fairness and circulating round robin, et cetera. So priority scheduling may give some people faster priority, more priority than the other. At the other end of the spectrum, you've got things like net neutrality, which argue against doing that. So hot issues happen inside these cars, believe it or not. Output port queuing is related to the one that we looked at with head of line queuing, but this one is one where you fill up your output queue and there's no point in doing it. Well, if you don't have enough room for everybody, then why not just drop the guy over here when he comes in the door? Just make people aware. There's an RFC that tells you, believe it or not, how much buffer to buy. And it basically says you need 250 milliseconds worth of buffer delay if that's a typical round trip time, times the capacity for C. So if you've got a 10 gig link, you need to be able to buffer 250 milliseconds worth of data. So you need a 2.5 gigabit buffer. That's a lot of memory. And with more recently, a change to that RFC has suggested that you can sort of tamp that down a little bit and divide it by the square root of the number of flows that you've got going on and conserve a little bit more. There's a bunch of scheduling mechanisms that we deal with. One of them is a discard policy, which we just talked about. Tail drop is drop the arriving packet if you're not going to have room. Just get rid of it right now. Don't bother keeping it around. Priority is use some scheme to select who should stay and who should go. And then you can have randomness, which is kind of my favorite because it's fair. And so this is all FIFO scheduling otherwise. You decide what to send out on the link next. Here's an example of a router that's had two different queues set up. One of them is a priority queue, and the other one is not. And so you've got rivals and arriving packets. They get dumped into one queue or the other, and your server, your link, will kind of get these things multiplexed and sent out the door as you hand them off. So it's up to you running these buffers to decide which one the link sees next. Which one does he get? And you can have lots and lots of these classes. You can have lots of decisions that you get to make, but let's walk through a little bit of an example of one. So I have two reds and one green packet that arrive. I send the red packet number 1, then I send red packet number 3, maybe because I have prioritization, and then I send green packet number 2. Meanwhile, while that's being sent, red 4 shows up, so I send him. Nothing happens for a while. Green 5 shows up, I send him, etc. And this is an example of round robin queuing. Round robin queuing may be what happens at the airport when they've got several different lines at the passport control, and the person's calling a person from the left line, middle line, right line, left line, middle line, right line. You can do things like that, or merging at an intersection. How do you decide who gets to go next? You're trying to figure out how to merge in there. So another variation that's very popular is called weighted fair queuing, and this is using the same kind of a round robin effect, but here you're very careful not to let one high priority queue starve everybody else out. If it always has data and you could always be sending something, doesn't mean you always should. Right? It means you do need to be fair so as not to have a starvation algorithm, because you'll get thrown off the boat yourself if you do stuff like that for very long. Okay, we need to continue on a little bit further into the next lecture slides and take a peek a little bit more about what's happening now inside the protocol itself. So here's one depiction of the bottom 4 layers of your 5-layer IP stack, TCP IP stack. The layer that's missing is the application layer at the top. We've talked about that. We've also talked about TCP and UDP in the transport layer. And what we see here is there are several different programs running inside this network layer to get the various pieces of the task done. Your routing protocols run in here. IGMP, ICMP run in here. ARP runs in here. The IP protocol itself runs in here. So there's some critical programs for the functioning of the network that are all considered part of the same layer. This is not some monolithic, gigantic, single piece of code that does all the stuff at once. There's separate blocks of code that get these things done. All protocols have a habit of being drawn out as a rectangle that's 4 bytes wide and some undetermined number of rows long. 4 bytes wide, I hope I said. So here's such an example for the IP header. I have a prettier version of this that I like to use that I can give you guys if I can get it to, I think I had to reboot, so it may take this a minute. I'll continue on with this for now. So you've got 1, 2, 3, 4, 5, 6 rows of header plus any possible options. The options may take 0 rows. They may take quite a number of rows. And what I want to do now is see if I can open up this. Here we go. Whoops, almost had it. IP header table. Okay, there it is. So I can blow this up a little bit, but I made it an Excel table so I could actually type values in and not have to try to sketch this out every time in PowerPoint or on a napkin or something like that. Okay, so 32 bits wide, number of rows long. I've sort of numbered the bytes, first byte, second byte, third byte, fourth, fifth, sixth, seventh, eighth, etc. And you can decode what's in one of these things by looking, for example, at Wireshark. You can pull a packet off of Wireshark, and it will tell you what every one of these fields are. All right, but the purpose of showing it here in the book at this point is to try to describe what these fields are. This tells you the IP protocol version number. For us, it'll mostly be 4 for IP version 4. You've got the length of the header in multiples of 4 bytes because that's the way we chose to use this set of 4 bits. And you've got a type of service field, which has a little bit to do with prioritization. You've got the number of hops left that this packet can make before you're going to throw it out the door and say, you've been running in circles, get out of here, and sending an error message back to complain to the original sender. Type of service talks about the type of data. Upper layer says, is this going up when I'm done with it? Am I sending the results up to TCP or UDP or what exactly? Total length of the datagram minus the header length gives you the payload length. Fragmentation we'll talk more about, and you can have some options in here, 0 to 40 bytes worth of options as well. All right, one of the things that this will do, that IP affords us the opportunity to do, is to divide big packets up that are too big to go on the network. And I was showing students an example of this earlier today, and I wonder if I can remember the website. Yeah, I can. There's a web page that has a list of all of the unencrypted websites that they can find around the world that are decent, and this was one of them. But they're all interesting like this. They're all kind of strange. So what I want to do is open up Wireshark and filter for HTTP packets. Come on. Running this may slow me down for a minute, make my audio sketchy, but I'll just take a moment. I'm going to do this and then reload that page. So, oh, I don't want to do Ethernet. Darn it. I want to do something else. Nope. Dadgummit. Oh, I did the wrong one. I'm not on Ethernet. I'm on Wi-Fi right now. All right, let's try it again. This time with feeling. Okay, and then I'm going to rerun this, and you will see some HTTP packets showing up. So I will stop this, and what we're going to do is take a peek at some of these responses. And what I want to find, so now I've cached all this stuff, so it's going to kind of hide it. But here is an example. What this is showing me is that I got a web page back. It actually was an image. It was a JPEG image that was on this web page. So whatever that page was I looked at a minute ago, one of these things on here was an image. Maybe it's this little, what is it, a rabbit, a squirrel? Who knows what it is? But it could not arrive all in one packet. And so what Wireshark did, as a courtesy, it went ahead and grabbed the ones that it came out of, packets 578, 79, and 80, And I don't even see them here anymore. They've been filtered off. So I'm going to turn off all my filters. And here they are. What was it again? It was 570, 78, 79, and 80. So these three right here. So this had the first batch of data, and this had the second batch of data, and this had the third batch of data. And at this one, it knew what was going on. Right? So these were 3 fragments that were sent over. So fragments happen all the time, and it's the responsibility of this IP layer to do whatever fragmentation might be needed. Right? So that's its job. Okay. So I send something over to a router. It's too big. It breaks it into 3 different ones. They will make their way across the network at that point as completely independent, full-fledged, card-carrying, header-spouting IP packets with destination addresses, links, flags, versions, the whole nine yards. They'll just be broken up separately so they can get routed in whatever their own little way might be different from the other ones. It all gets reassembled, comes back together at the host at the end, and you rebuild your original datagram. That's the idea. You do reassembly to get it done. So we know whether fragmentation is happening or not because there are some important flags in the IP header. So if I pull up my header again, I say, if I pull up my header again, it's not going to pull it up. Let's see what it's doing here. Let me see if I can get it to come up this way. Yeah, I have spots for 3 bits in here. Do not fragment, more fragments, and fragment offset in octets. All right, so if I have a 4,000 byte datagram, it's trying to go on a network that can't handle more than 1,500 at a time. It's going to need to be fragmented. So I'm going to break it into 3 packets. The first one is 1,500 bytes, the second one is 1,500, and the last one is 1040. So that's 4,040. How in the world does that equal 1,500? So it's because there's some 20 bytes of header in there that's part of that as well. So each of these carries a part of the story. And the way fragmentation works is you remember the length of the packet. So you put that in there. It's a new packet now. You've broken it off the others. You set its identifying number, serial number, to be the same as the original, so you know whose pieces you're receiving at the other end. Might be in the middle of a file. You're not going to be able to tell by looking at that. And so that ID number, like a serial number, will help you know what pieces to put back together. You may be getting fragments for lots and lots of packets at the same time. The fragment flag is going to be set to 0 in this case, basically saying, I am not the last fragment. Okay, and the next guy will say, I am not the last fragment. The last guy will. He will be the last fragment. The last thing in here is the offset. Okay, so if you took my packet and you broke it up into pieces, how am I supposed to know how to put you back together? So each of these will show up and say, put me in there starting at byte number, and then it'll give you a number, and that's basically what's encoded in this field here. So these happen to be 3 contiguous ones, very lucky. None of them got lost. None of them got arrived out of order. So I got 0, I put it down. I got the one that starts at 8 times 185, I put that down. I got the one that starts at 8 times 270, put it down. Presto, I have my whole thing back together again. Wireshark will announce to you, you have a packet, congratulations, and you send it on up. So we'll need to take a look at some fragmentation a little bit more to really understand this stuff. Okay, let me take a peek at where we are, because this is too much. Ooh, let me inch my way into it for a minute, just for a minute. All right, I like the way this book draws its network diagrams far better than the advanced TCP/IP text that I teach out of as well, for the very simple reason that he's relatively careful, not great, but relatively careful about drawing the LANs, and is great at putting the IP addresses where they belong. The IP address belongs to the port on a router. I repeat, bulletin this just in, every router port has an IP address because every router port belongs to a subnet. So if you draw me a router with 3 ports, You need to give me 3 IP addresses from 3 different subnets. Right? Very important. Don't act like you didn't hear that. Right? So we just covered it. It's something that if you listen, you'll grasp the very first time. If you don't, you're going to do me to repeating it. And I'm okay repeating stuff, you know, once in a while. I just don't want to have to do it 10 times in a row. If I saw you goofing off and you're asking then, that's like different than if it just was too much to absorb. Wow, that's like me. I totally can relate to that. Okay, so let me clean this up a little bit. And we're going to make a couple of corrections to make it not just great, but perfect. All right, turn off my thing here, and I'm going to grab my color wheel. I'm going to grab exactly the same color. So the LAN that the router port belongs to needs to color in the router port as well. That would be nice. And it needs to include all the hosts. Presto, that one's done. This one needs to include the router port as well. So if you're going to draw a polygon, you know, make the polygon touch this. And the last one is something that looks more like this. All right, what I do not like is when people draw something that looks like this, and this, and you don't really have any idea what it's belonging to, or God forbid, if I catch you doing like this. No, you've got 3 ports in there at once. So this is the only slight upgrade I would make to the diagram that they have in here. And you can see these funny numbers here, number dot number dot number dot number. Those are IP addresses, Internet Protocol addresses. And it's just the number, the unique number that's assigned to the device. So your phone has one, your tablet has one, your laptop has one, your PC at office or home or wherever has one. They all use IP addresses. Okay, that's a decent stopping point for now. I will have a homework out. It's written. I got to get one thing straightened out that's kind of messed up on it, but as always, I'm backed up, but I'm trying to crank it out for you guys fast. I will see you in class in person on Monday. Welcome back. See you guys. Let me look at the chats. Light Towers of Hanoi. Yes, it's exactly like that. Very good. All right, what else do I have here? That's it. Quit out of that, and I think we're ready to go.